Welcome to Sri Learning Academy. Let's simplify shared memory. When we talk about interprocess communication, we have already seen that processes usually live in their own separate memory spaces. This isolation is important for safety, but it creates a problem when processes need to cooperate. In the previous discussion on IPC, we briefly compared message passing and shared memory. Message passing works like sending letters back and forth through the operating system. Shared memory, on the other hand, is more like two people writing on the same whiteboard. In this video, we will focus entirely on shared memory and understand how it actually works inside an operating system using simple and practical examples. To begin with, shared memory is an IPC technique where two or more processes are allowed to access the same region of physical memory. Normally, each process has its own private address space, as we discussed earlier while talking about processes and memory protection. A process cannot directly read or write another process's memory. Shared memory is a controlled exception to this rule. The operating system deliberately creates a memory segment and maps it into the address spaces of multiple processes. Once this mapping is done, all those processes can read from and write to that shared region. Think of it like this. Imagine two offices in the same building. Normally, each office has its own locked storage room. No one else can enter it. Now imagine the building manager creates a common meeting room with a shared table. Both offices are given keys to this room. Anything placed on the table can be seen and used by both offices. That shared table is similar to shared memory. The operating system is building manager who decides who gets access. One important point to understand is that shared memory itself does not handle communication logic. It only provides a common space. The processes decide what data to put there and how to interpret it. This makes shared memory extremely fast. Unlike message passing, where data has to be copied from one process to the kernel and then to another process, shared memory avoids repeated copying. Once the memory is shared, processes directly access it. This is why shared memory is considered the fastest IPC mechanism. Let us take a simple real world style example. Suppose you have one process that reads data from a file and another process that processes that data. For example, imagine a video streaming application. One process reads video frames from disk or network, and another process decodes and displays those frames. If these two processes use message passing, each video frame would be copied again and again. This is inefficient. With shared memory, the reading process places the video frame into shared memory, and the decoding process reads it directly from there. No extra copying is needed. Performance improves significantly. Now let us talk about how shared memory is actually created. A process cannot simply decide to share memory on its own. It must ask the operating system. This is usually done using system calls. In Unix-like systems, calls such as shmget, shmat, and shmdt are used. You do not need to memorize these names right now. What matters is the idea behind them. First, a shared memory segment is created. Then, processes attach this segment to their address space. When a process is done, it detaches from it. Finally, the OS can remove the segment when it is no longer needed. From the process point of view, once the shared memory is attached, it looks just like normal memory. The process can use pointers, variables, arrays, and structures on it. There is no special instruction required to read or write shared memory. This simplicity is powerful, but it also introduces new challenges. To understand those challenges, imagine two people writing on the same whiteboard at the same time. If they do not coordinate, one might erase what the other just wrote. The same thing can happen in shared memory. If two processes write to the same memory location at the same time, the result can be unpredictable. This is known as a race condition, a topic we will explore deeply in the synchronization module. For now, it is enough to know that shared memory almost always needs synchronization mechanisms like semaphores or mutexes. Let us look at a classic example that connects shared memory with synchronization. Consider the producer-consumer scenario. One process is the producer. It generates data. Another process is the consumer. It uses that data. They both use a shared buffer in memory. The producer writes data into the buffer and the consumer reads from it. Shared memory makes this efficient because both processes access the same buffer. But what if the producer writes new data before the consumer reads the old data? Or what if the consumer tries to read when the buffer is empty? These problems are not solved by shared memory itself. They are solved by synchronization tools, which is why shared memory and synchronization are often discussed together. Now, let us walk through a very simple step by step example to make this concrete. Imagine a shared integer variable called count stored in shared memory. Process A increments this variable whenever it produces an item. Process B reads this variable to know how many items are available. If process A writes to count while process B is reading it, process B might see a half updated value. This sounds strange, but at the hardware level, it can happen. To prevent this, both processes must agree on rules. For example, they might use a semaphore to ensure that only one process accesses count at a time. Another important aspect of shared memory is lifetime management. Unlike normal process memory, shared memory can exist even after a process exits. If the operating system does not clean it up properly, shared memory segments can remain allocated and waste system resources. This is why systems provide explicit ways to remove shared memory segments. It is also why shared memory is considered a more advanced IPC technique. It gives more control but also more responsibility. Let us briefly compare shared memory with message passing again. Message passing is easier to reason about because the OS handles synchronization implicitly through send and receive operations. Shared memory gives better performance, but the programmer must handle synchronization manually. In practice, shared memory is preferred when large amounts of data must be exchanged frequently, such as in databases, multimedia systems, and high performance servers. To summarize everything in simple terms, shared memory is a powerful way for processes to communicate by sharing a common space in memory. It is fast because it avoids unnecessary copying. It is flexible because processes can organize data in any format they want. But it is also dangerous if used carelessly because multiple processes accessing the same memory can interfere with each other. This is why shared memory is usually combined with synchronization tools. When used correctly, shared memory enables efficient and high performance communication between processes, making it a key concept in modern operating systems. That is it for this video. See you in the next one.